Bismillahir Rahmanir Rahim. Start with the name of Allah, who is the most merciful and most gracious. Today our topic is about how to design a simply supported beam. The question is, a reinforced concrete simply supported beam has a span of 30 feet and support the service dead load of 1000 lb per feet and uniform service live load of 1100 lb per feet. So the design beam section to resist the factoral external bending moment, which is that Fc prime is equal to 4000 psi and Fy is equal to 6000 psi. So first of all, the given data we have taken from that question is length is equal to 30 feet, dead load is equal to 1000 lbs per feet, which is equal to 1 caps per feet. Uniform dead load, live load is equal to 1100 lbs per feet, which is equal to 1.1 caps per feet. Fc prime is 4000 psi and Fy is equal to 60,000 psi. The required data is what? The required data is beam section to resist the external load bending moment. Solution. The solution, we start, the first step is how to give the size to that beam. The length has been already given in the question and we just have to find the depth and breadth of that section. So the depth is always we can find that depth from L by 16. The formula is for this simply supported beam Fc prime is equal to Fm is equal to 60,000. The formula is length divided by 16, so we will get the depth. So that is 30 our length and 12 we multiply for what, for to change that length into inch by 16 we get 22.5 inch. So we will consider that the beam has 24-inch depth because this is just the assumption and this steps. For width we need to do that what the height has come, we will just divide that by 2 and we get the breadth. But remember that the minimum required width of the beams that SI give us shall not be less than 12 inch. That's why we got it 12 inch. So move to find that what is the effective depth of that beam. So we have the formula that H is equal to D by that Y prime. We got Y prime is equal to 3 inch. So D is equal to H minus Y prime. D is equal to 24 minus 3. We get the answer, which is 21 inch. The effective depth of the beam shall be 21 inch. But these all are the assumptions. Next steps number 2 in the design is to find the total load applying on that beam. So we have the formula that 1.2 into dead load plus 1.6 into live load. We get that 1.2 into 1 is 1 caps per feet plus 1.6 into 1.1. The answer, the total depth of the total load applying on their beam is 2.96 caps per feet. Next step is analyzing that what the total movement comes in that beam. The movement is the formula we have for the simply supported beam, that is load multiply length square by 8. The load is we also given 2.96 multiply 30. 30 is the length of the beam. We take square on that, multiplying that whole multiplying with that 12, we get divide by 2. So we will get the answer from this equation, that is 3996 caps into inch. This 12 multiplying with this factor we change that feet into inch. Step number 4, design a flexor. And this is the design step started from here. This is very important. Assume A is equal to 4. This is just assumption. We just assume that is equal to 4. So first rail, the area of steel formula is mu by pi Fy into D minus A by 2. That is mu, the given moment. and 0.9 is that factor. 60 is what? 60,000 Fy is equal to 60,000 prime. So we divide that with 6,000, that is 60,000 caps. 21 is the effective depth minus 4. We assume that A divided by 2. By doing all these calculations, we get that area of steel is equal to 3.89 inch square. So we will put this area in that A to find whether we select that 4 is equal to A is right or not. So we put that AS is equal to, the area is AS by Fy into 0.85 FC prime BW. We put that FC prime is 400 PS, 4000 PSI. We divide that by 1000, we get 4 kips, and 0.8 the factor, and B is the width of the beam. Putting all these value in this equation, we get that A is equal to 5.75. But there is a change that we assume and this. So we will do the second trial. All these equations are fine. At the same equation, we will put the values, but just there is A, we put that the value here also of A, but the value was 4. But here we will put the value which we get from this equation, that A is equal to 5.72. We put it here, doing all the calculation, get the value of area of steel, which is equal to 4.1 inch square. Now going further, we will put this area of steel in that A to get the A equation. So value, we put that A is equal to S by Fy divided by 0.8 FC prime B. 4.1 the value of AS, 60 is the Fy prime, 0.87, 4 is Fy FC, and 12 is the width of the beam. We do all equation, we get that A is equal to 6.03. So we see that there is A is equal to 6.03, and the A here is equal to 5.72. We will do another trial to get close to the correct value. So the next trial, all the things are same, just taking that formulas, putting the value. But here the A must be changed. We will put the value of A which we get from the second trial. We put that value here, and doing all the calculation, get the value that area of steel is equal to 4.12 inch square. We will put again this area of steel in to find out the correct A. We do all the calculation, AS Fy by 0.85 FC into B. We get that A is equal to 6.1. So enough close to the previous trial. So we select that our A was the second trial. We can also get the value from second trial and also from the third trial. So, but just we get the value from that second trial, which area of steel was 4.1 inch square. So now we will do that. Area A is minimum. So the formula is 3 into FC prime by Fy into BD. Area of steel minimum. But remember, when we put the value of FC prime and Fy in this formula, it shall be that in PSI, not in KSI. If we put that in KSI, so the value will be wrong. So we will just put the value of FC prime was 4000 by FC prime, the Fy is equal to 60,000. Doing all the calculation, remember that FC by Fy is whole under root. We will do all the calculation and get the area of steel minimum, that is 0.796 inch square. Second formula for area of steel minimum, that is 200 by Fy into BW. BW is what? Width of the beam, and D is depth. So we just put the value. Fy 60,000, 12 is width, and 1 is effective depth of the beam. So the area of steel minimum is 0.84 inch square. Remember, the value which we get from as minimum, both these formula, the value which one is bigger, we will take that, compare our value with this. So we will compare the value of area of steel with this. Okay, area of steel maximum formula is very easy, 0.3 into FC prime by Fy into BD. 0.3, we will put that in KSI. Why? Because the formulas here, the 0.3 factor, I think this affect that formula. That's why we put 4000 here and 60,000, and we will just put here 4 and 60. Maybe this 0.3 affect their formula, and we will get the area of steel maximum, that is 5.04 inch square. Now comparing our value which we get from second trial, AS minimum was 0.84 and area of steel which we get, that was 4.1, and area of steel maximum 5.04 inch square. So it means that our calculation was right, the area which we find for the steel was correct. So next step is placement of bars. So we select from a SI table that we get 6 number 8 bars, which area is equal to 4.7975 area in square, so which is quite better from our find area. So it means that we are in safe mode, so we select that. Now flexure capacity, to check, we shall check that whether our calculation or our design is good or not, or will it take the load which apply on this or not. So finding the effective depth. So there is a quite a little diagram which give the how we place our bars. So we place 4 number 8 bars at the bottom, 2 number 8 bars at the middle. Not at the middle, the distance between this bar and this bar shall not be less than the area of 1 bars. That is clear. And this is for just supporting the stirrups of the beam. So we find that Y is equal to 1.5 concrete cover plus 3 by 8 the area of stirrups plus 0.5. 0.5 is half area of number 8 bars. We put that, we get Y1 is equal to 2.7 inch. Y2, which is here, so 1.5 same cover of concrete, 3 by 8 stirrups plus 1 distance between this and this steel bars, that is 1 inch, plus 1.5 plus 0.5 area of this half area of the bar. So Y2 is equal to 4.87. Now to get Y dash, we will, that is 6 multiply 0.79. 6 is number of bar, total number of bars. 0.79 is what? The area of 1 bar, multiply Y dash. 4 in the first number of bars in the first row, multiply area of 1 bars, multiply 2.737. 2.37 is a factor, plus 2 number of bars, multiply area of 1 bars, multiply 4.87 is this Y2, and this 2.17 was Y1. We do all the calculation, changing that is equal to this, convert this Y here, and when we convert this to there, it will be divided, we get the Y dash value which is equal to 3.92. We find the effective depth at the top of the lecture, but here the effective depth, that was assumption, but this is what, this is accurate effective depth, which is D is equal to H minus Y dash. H was 24, Y dash is 3.2, so we get 20.8 the effective depth, but we take the assumption which was 21 inch. Not much difference. Now area of steel, so 6 number area of steel, this 6 number 8 bars area is equal to 4.74. You can also calculate that, but area A, to find A, we put we have the formula area of steel Fy divided by 0.85 Fc plus multiply B. We will just put these values. Area of steel is 4.75, 60, get that A is equal to 6.97. Now we have to find that whether our calculation or our design is fine or not. So here Mn is equal to Phi As Fy to D minus A by 2. So that is the factor 0.9 As area of 6 number 8 bars, which is equal to 4.74. Fy is equal to 60. D, the effective depth. Here we will put that 20.8, which we find here, not that 21. Clear? And A is also we find here, that is the accurate. The effective depth is also accurate, and this A is also the accurate one. So we will put that accurate value and this value to check whether our calculation or our design is safe or not. So we put that being all the calculation, get the values of ultimate moment, that is 4431.94 kips into inch, which means our design is okay. How? Look at there. This values which we got from for the check is bigger than the capacity. This is demand. Clear? The value mu is demand, and this is the capacity which the beam will take. So the demand is less than the capacity, which means that our design is okay. Wish you good of luck. Subscribe the channel and also like.